A few minutes ago, roughly 3 billion miles from where you're sitting right now, a tiny world at the edge of our solar system was quietly doing something no planet has any business doing. It was losing heat it shouldn't be able to lose, staying colder than physics says it should ever get. And for almost a decade, nobody could explain why. Then the James Webb Space Telescope pointed straight at it and confirmed an idea so strange that most planetary scientists initially wrote it off as impossible. Stay with me, because this is a real, published 2025 discovery, and it's genuinely one of the strangest climate systems ever found anywhere in our solar system. Subscribe now, because we're about to break down exactly what Webb found and why it matters. Let's rewind to 2015 first, when NASA's New Horizons spacecraft became the first and only mission ever to fly past Pluto up close. Scientists expected a barren, unremarkable little world. What they actually found was towering mountains made of water ice, smooth plains of frozen nitrogen stretching for hundreds of miles, and hanging above all of it, something nobody anticipated: a thin, delicate haze wrapping around the entire planet like layered blue silk. This haze wasn't dense, but it extended nearly 200 miles above the surface, far higher than anyone expected a small, distant world like Pluto could sustain. But the real puzzle wasn't the haze's beauty. It was Pluto's temperature. Based on standard atmospheric models, factoring in how much sunlight actually reaches a world this far from the sun, and how nitrogen and methane gases typically behave, Pluto's atmosphere should have settled at a certain predictable temperature. Instead, the real measurements came in dramatically colder, roughly 30 degrees miles below what the models predicted. That's not a small rounding error. That's the kind of gap that tells you your underlying model is missing something fundamental. For years afterward, researchers reran calculations, recalibrated instruments, and rechecked the New Horizons data from every possible angle, and the numbers simply refused to add up. Something was pulling extra heat out of Pluto's thin atmosphere, and nobody could identify what it was. In 2017, a planetary scientist named Xi Zhang at the University of California, Santa Cruz, proposed an idea that struck many of his colleagues as genuinely far-fetched at the time. What if Pluto's haze wasn't just a passive decorative layer sitting quietly in the atmosphere? What if those microscopic solid particles were actively controlling the planet's entire energy balance? Zhang's theory suggested these tiny haze particles could absorb incoming sunlight and then re-emit that energy, not as visible light, but specifically as mid-infrared radiation, essentially heat escaping directly into space. If that were true, the haze wouldn't just reflect a bit of sunlight the way scientists assumed. It would function almost like an active thermal radiator, bleeding heat away from the planet far more efficiently than ordinary atmospheric gases ever could. And that extra heat loss could fully explain Pluto's mysteriously cold atmosphere. Many scientists at the time were skeptical. The idea that solid particles, rather than gases, could dominate a planet's atmospheric temperature control cut against a lot of standard planetary science. But Zhang's theory came with a specific, testable prediction attached. If his idea was correct, Pluto's haze should be glowing faintly in a very particular range of mid-infrared wavelengths, a signal so faint that only one instrument in existence would ever be sensitive enough to detect it: the mid-infrared instrument, or MIRI, aboard the James Webb Space Telescope, which hadn't even launched yet. That opportunity finally arrived in 2022 and 2023. An international research team led by astronomer Tanguy Bertrand at the Paris Observatory pointed Webb's instruments directly at Pluto and its large moon Charon. This mattered enormously because Charon orbits so close to Pluto that earlier telescopes, including the Spitzer Space Telescope and the European Space Agency's Herschel Observatory, had already detected faint mid-infrared emissions coming from the Pluto-Charon system going all the way back to 1997. But none of them had the resolution needed to tell which world the signal was actually coming from. Webb, with its considerably larger mirror and far more sensitive instruments, finally had the precision to separate the two signals for the first time in history. Using MIRI, the team scanned across multiple infrared wavelengths, and the results were striking. Pluto's infrared glow was noticeably stronger than its frozen surface alone could explain. Once researchers subtracted Charon's separate contribution from the combined signal, isolating Pluto's atmosphere specifically, the remaining data matched Zhang's 2017 prediction closely. The haze wasn't simply scattering incoming sunlight around. It was actively glowing in mid-infrared wavelengths, radiating heat outward exactly the way his theory had predicted 6 years earlier. Zhang himself later said, "It isn't common in planetary science for a hypothesis to be confirmed this cleanly within less than a decade of first proposing it, and that the team felt genuinely fortunate to see it happen." The research, led by Bertrand, along with Zhang and his former graduate student Linfeng Wang, was formally published in the journal Nature Astronomy in June 2025, officially confirming that Pluto's haze doesn't just decorate its skies, it actively governs the planet's climate. This finding meaningfully changes how planetary scientists think about atmospheric climate control in general. For decades, the standard assumption across planetary science was that gases drive a planet's climate. Carbon dioxide trapping heat on Venus, methane shaping the thick atmosphere of Saturn's moon Titan, and so on. Pluto turns out to be something different. Here, solid particles, specifically a class of compounds called tholins, are effectively running the climate system instead. Tholins form when ultraviolet sunlight strikes methane molecules high in Pluto's atmosphere, triggering a cascade of chemical reactions that build up increasingly complex hydrocarbon compounds. As these particles slowly drift downward through the atmosphere, they build up in layers, forming the haze that both scatters visible light, giving Pluto its subtle bluish glow, and radiates heat away in the infrared, cooling the atmosphere from above in a way that's genuinely unique among the worlds we've studied so far. Bertrand has described the resulting phenomenon as a completely new kind of planetary climate, distinct from anything else observed in our solar system. And the discovery didn't stop with temperature alone. Webb's data also revealed that methane escaping from Pluto's thin atmosphere is drifting through space and settling onto the surface of Charon, where sunlight then converts it into the reddish organic compounds visible at Charon's poles. In a very real sense, Pluto is slowly depositing material onto its own moon and altering its surface chemistry over time, a genuinely unusual interaction that researchers say appears to be unique within our solar system. Once this haze-driven cooling mechanism was confirmed at Pluto, researchers naturally began wondering whether similar processes might be happening elsewhere. Zhang has pointed specifically to Saturn's moon Titan and Neptune's moon Triton as worlds that share broadly similar nitrogen and hydrocarbon-rich atmospheres, meaning the same fundamental haze chemistry could plausibly be playing a comparable role there too, giving researchers a genuinely valuable new framework for understanding how haze behaves in these kinds of extreme, frigid environments across the outer solar system. There's also a genuinely compelling connection to Earth's own deep history buried in this discovery. Zhang has pointed out that before oxygen accumulated in Earth's atmosphere roughly 2.4 billion years ago, our own planet's atmosphere was dominated by nitrogen and hydrocarbon compounds, chemically not entirely unlike what we currently observe on Pluto today. Studying how haze particles regulate temperature and chemistry on Pluto right now may end up teaching researchers something genuinely useful about the chemical environment on early Earth, long before life, as we know it, eventually took hold. Before diving deeper into the haze itself, it's worth stepping back and remembering just how remarkable it was that we had any close-up data on Pluto at all by 2015. Pluto was discovered back in 1930 by American astronomer Clyde Tombaugh, working at Lowell Observatory in Arizona after a painstaking search for a predicted planet X, thought to be influencing the orbits of Neptune and Uranus. For decades afterward, Pluto remained little more than a faint, blurry point of light, even through the most powerful telescopes available, simply too small and too distant to resolve any real surface detail. In 2006, the International Astronomical Union controversially reclassified Pluto as a dwarf planet rather than a full planet, a decision that remains genuinely debated among astronomers and the public alike to this day, though it doesn't change anything about the science itself. NASA's New Horizons spacecraft launched in January 2006 specifically to finally get a close look at Pluto, and it took more than 9 years of travel, covering roughly 3 billion miles before it finally reached its target in July 2015. Because Pluto is so far from the Sun, New Horizons couldn't simply slow down and enter orbit the way missions to closer planets often do. Instead, it performed a single, fast flyby, gathering as much data as possible during a brief window of close approach before continuing onward into the distant Kuiper Belt. That flyby remains, to this day, humanity's only close-up visit to Pluto, and everything we've learned since, including this haze discovery, has come from analyzing that dataset alongside remote observations from telescopes back here in our own solar system. It's worth appreciating just how different Pluto turned out to be from what scientists expected going into that 2015 flyby. Many researchers anticipated a fairly simple, geologically dead world, similar to how the moon appears from a distance. Instead, New Horizons revealed young, active-looking terrain, including a massive, smooth plain of nitrogen ice now known as Sputnik Planitia, roughly the size of Texas, along with mountain ranges made of solid water ice, since regular rock would be far too soft to remain rigid at Pluto's extreme surface temperatures. Evidence also pointed toward ongoing geological activity, meaning Pluto isn't simply a frozen, unchanging relic, but a world that continues to slowly reshape itself even today, billions of miles from the Sun. Charon, Pluto's largest moon, turned out to be nearly as interesting in its own right. It's unusually large relative to Pluto itself, roughly half of Pluto's diameter, which is part of why the two are sometimes described as forming a binary system rather than a simple planet and moon pairing. Unlike Pluto, Charon lacks any significant atmosphere of its own, though the newer Webb research suggests it may experience some seasonal outgassing. Its surface is dominated by water ice mixed with ammonia-based compounds, and its most visually striking feature is a large reddish patch at its north pole, formerly nicknamed Mordor by the New Horizons science team. It's precisely this reddish coloring that Bertrand's team has now connected directly to methane, escaping from Pluto's atmosphere and settling onto Charon's surface, where solar radiation gradually converts it into the same kind of complex organic tholin compounds responsible for Pluto's own haze. Let's go a little deeper into how researchers actually measured all of this using Webb, because the technical process itself is genuinely impressive. The mid-infrared instrument, MIRI, is specifically designed to detect longer infrared wavelengths that are extremely difficult to observe from Earth's surface, since our own atmosphere absorbs much of this radiation before it ever reaches ground-based telescopes. Operating from space, well beyond Earth's atmospheric interference, and cooled to extremely low operating temperatures to minimize its own thermal noise, MIRI can detect incredibly faint heat signatures from objects billions of miles away. In this case, researchers specifically measured Pluto and Charon across a range of wavelengths between roughly 5 and 27 microns, far beyond what the human eye can perceive, capturing subtle variations in thermal radiation as both worlds rotated. By comparing how that radiation changed over the course of Pluto's roughly 6.4-day rotation period, researchers could map out variations in temperature, thermal inertia, and surface composition across different regions of both worlds, and crucially, isolate the specific contribution coming from Pluto's high-altitude haze layer rather than its surface ice. This kind of long-term, carefully calibrated observation simply wasn't possible during New Horizons' brief 2015 flyby, which prioritized capturing detailed images and surface composition data during its short window of closest approach, rather than sustained thermal monitoring over multiple rotations. That's precisely why it took a dedicated space telescope like Webb, capable of returning to observe Pluto repeatedly over an extended period from Earth's vicinity, to finally test and confirm Zhang's decade-old theoretical prediction. It's also worth touching on why researchers care so much about comparing Pluto to Titan specifically, beyond just their shared nitrogen and hydrocarbon atmospheric chemistry. Titan, Saturn's largest moon, has actually been studied in far greater detail than Pluto up to this point, thanks to NASA's Cassini spacecraft, which spent 13 years orbiting Saturn and repeatedly studying Titan up close, including landing the European Huygens probe directly on its surface back in 2005. Titan's atmosphere is considerably thicker and more complex than Pluto's, complete with actual liquid methane lakes and rivers on its surface, something Pluto's much thinner atmosphere and colder temperatures don't currently support. But the underlying photochemistry that builds up haze particles in both atmospheres appears to follow genuinely similar chemical pathways, meaning insights from one world can meaningfully inform researchers' understanding of the other, even though Titan and Pluto differ enormously in size, atmospheric thickness, and overall environment. Looking ahead, researchers are hoping to secure additional observation time with Webb to continue monitoring Pluto's haze and atmosphere over a longer stretch of its 248-year orbit around the Sun, since Pluto's atmosphere is known to change somewhat as it moves through different points in that extremely long orbital path, expanding somewhat when it's closer to the Sun and thinning as it moves farther away. Continued monitoring could help researchers understand not just the current snapshot of Pluto's climate, but how this haze-driven cooling system responds and adjusts over much longer timescales, adding an entirely new dimension to our understanding of one of the most distant, and now, thanks to this research, genuinely one of the most scientifically interesting small worlds in our entire solar system. It's genuinely worth being careful and precise about what this discovery does and doesn't mean. This is real, carefully measured, peer-reviewed atmospheric physics and chemistry, not evidence of anything artificial or engineered sitting on or beneath Pluto's surface. The finding is remarkable specifically because it reveals a genuinely novel, naturally occurring climate mechanism, solid particles actively regulating an entire planet's temperature and driving material transfer to a neighboring moon, something we hadn't confirmed happening anywhere else in the solar system until this research came together. That's precisely what makes it worth understanding properly, rather than needing any embellishment to feel significant. Researchers are also actively exploring whether similar haze-driven cooling mechanisms might extend well beyond just Pluto, Titan, and Triton, potentially even applying to certain exoplanets outside our own solar system, worlds with hydrocarbon-rich atmospheres located in cold, dim outer regions of other star systems. If particles, rather than gases, can regulate a planet's overall temperature this effectively, that could meaningfully change how researchers model climate stability on other cold, distant worlds we're only just beginning to study through next-generation telescopes. This is still a genuinely active, ongoing area of research, and much of the broader exoplanet connection remains speculative and still being tested rather than confirmed. But Pluto's case gives researchers real, physically grounded evidence that this kind of particle-driven climate control is possible in nature, not merely theoretical.